Hi, today I am going to talk about my project Understanding Memory Networks to Complete AI Task for Question Answering. So let's see what the problem statement is. So the problem statement is basically a question answering task. So we have been given a set of statements and after that we have been asked a question. So we have to answer that question based on the text given previously. For example, let's see the example given in the slide. John is in the playground. Then the second sentence is Bob is in the office. The third sentence asks the question where is John? The correct answer is playground. Let's see another example. It says John is in the playground. Bob is in the office. John picked up the football. Bob went to the kitchen. So where is the football? So the correct answer is playground. So to infer this answer, you can see that we need to combine the two statements John is in the playground and John picked up the football, which essentially means that the football is in the playground. So such a task is called a task with two supporting facts. Similarly, we have been given a list of categories of different tasks in the Facebook babi dataset from which we derived our data. So let's look at what solution was proposed. So the solution is memory networks. Memory networks were introduced in 2014. It were presented in ICLR in 2015, and the authors of the paper were Jason Wesson, Sumit Chopra, and Antoine Baudes. So, what is memory networks? It is basically a class of models that combine large memory with learning component that can read and write onto it. The concept is very simple. First, we have to store the text in memory. Next, we have to transform them by using embedding matrices. Now, we have to do computations on the transformed text over them to train the model. Let's take a look at the memory network's architecture. It has four components. First is called the input component, which converts the input to internal feature representation. Next is called the generalization component, which updates old memory slots, therefore generalizing the memory. Next is the output component, which gives new output given the input and the current memory state. Next is the response, where we convert the output into a response format. In this case, we have a text response. So where does machine learning come into picture? We are using deep learning in our project uh, using a model called end-to-end memory networks rather than the original model called the memory networks. So in end-to-end memory networks, the neural network accesses memory multiple times, each step being called a hop. It uses back propagation to update the model. This is the architecture diagram of end-to-end memory networks. We'll come back to it at a later stage. Let's see at some details of the model. So we have been given x1 to xn sentences. Then these sentences are embedded into memory vectors mi and ci by using embedding matrices a and c. Question q is embedded into an internal state u. So and after that the matching is performed between u and mi with the softmax function. Let's go back to the diagram once. If you can see, we have the question q which has been converted into the internal state u by using the embedding matrix b. Similarly, we have a set of sentences here xi which have been converted into mi, the memory vectors, using embedding matrix a. Uh, Now let's go back to the slide. So we perform a matching between u and mi with a softmax function. If you see, we got a u internal state and the mi memory vectors. Using the softmax function, we perform a matching between mi and u. So the next step is output is being calculated by the relation O equal to summation over I pi ci. So now we calculate the output O, which is nothing but a summation of our internal weight matrix pi, which was obtained after doing the softmax function, and the memory vectors Ci, which were obtained after converting sentences into the memory vectors. Now the next step is we have another softmax function which is used to produce the final prediction after summing up O with U. So if you see, we get O and we get U, and then we perform a summation, then we pass it through a W function, and finally we have a softmax function which gives us the predicted answer A cap. Now before going into the results, let's take a look at the code. So if you see the code has been written entirely in MATLAB, and the code has been taken from Facebook AI research team's original code on GitHub. So we have a file called run.babi.m, which is basically taking the data from the files, the training file and the test file, and then it is calling the functions which have been written in MATLAB. So it is calling parse babi task, which is basically parsing the data and converting it into internal matrices. Thereafter, after parsing the data and converting into the matrices, we configure the model by setting up various parameters. If you see, we have various parameters being set here, such as the batch size, number of hops, number of epochs, that is the number of iterations, learning rate, etc. etc. Apart from that, after this step we are calling the build model function, which basically builds the model by doing all the steps which we discussed before in the architecture diagram. So if you can see, it is adding and multiplying and doing element wise multiplication, and thereafter it is adding a softmax function finally to get the prediction A cap. So let's run the program once. For now I have taken t is equal to 1, which means the task ID is 1, which means we are talking about the single supporting fact task, and then let's see what happens. If you can see, the training has been started and the step-by-step validation error and training error is being calculated. So you can see a change in the index number. After 20 tasks, the index change 20 sentences. So this indicates that there has been a change in the story, and a story is nothing but a set of sentences which are like a packed unit within which you have a set of questions. So all the questions will be answered by the sentences within that story. This will take a while to run. So while this is running, let's take a look at the dataset, how it looks. As discussed before, we have a set of statements like 1 and 2, which give the text, and then the third statement asks a question to the machine, and then since this is the training set, we have the answer to the question, and we have 1. The 1 here indicates or the number here indicates that we have the supporting fact which is at line 1. Similarly, if you see the next two statements, Maddie went back to the bathroom and Mary moved to the hallway, we have the answer to the sixth statement, where is John, and then along with the answer we have 2. This 2 indicates that the supporting fact for this question lies in the statement number 2, and yeah, that's how the entire dataset is being organized. Now, as you can see, we got the test error which is 0. Take a look at the combined results which were published in the paper. You can see for task 1 the error rate is around 0 for PELSRN model, which is what we are running now. And let's go to task 2 and see what the error rate is. So I have changed the task to 2 and I ran this model once, and the error rate is coming out to be 9%, 9.2%. And if you look at the table, it is coming around 8.3 if you do an average over a number of instance runs. So uh, let's go to the results and inferences. By running this algorithm over a lot of models, we understand that the strongly supervised memory network is the one which gives the minimum number of error, minimum percentage of error, which is 6.7%, and the least tasks failed, which is only 4 tasks are failed in this model, uh, as compared to the unsupervised or the weakly supervised models, such as PELSRN, which gives 11 failed tasks and 13.9% mean error. Now let's go to the other results. We understand that the position encoding representation improves bag of words model, as demonstrated by improvements on tasks 4, 5, 15 and 18, where the word ordering is particularly important. So the position encoding model is laying stress or giving weight to the word ordering as well. However, the other models were not doing so. Hence, we saw improvements on tasks 4, 5, and 15 and 18. Also, if we were adding random noise and linear start to the model, it improved the overall efficiency of the model, which is also depicted in this chart. So that's it for now, and this is the list of references and the original paper of end-to-end memory networks, written by Seinberg, Weston, and others. And this is the link for the code. Thank you.